So the last day we derived the generalized uncertainty principle, but after sufficient time to discuss what it actually means. So let us start with that today. And we know that in case of the position and the momentum, it has a specific form. The sigma px is greater than equal to. Right. Now, when this particular equation was, or an inequation was first proposed by Heisenberg, there was a lot of confusion as to what it actually means. But what this actually means, that caused a lot of confusion, and that confusion still persists. If you read popular science literature, you will find that that confusion is in some sense still there. But then Bohr and Heisenberg, they sort of proposed a way of explaining this. They said that suppose you have got a particle somewhere, maybe in the harmonic oscillator well, and you want to find out its position. How do you find it? You find it by on that. And light means some electromagnetic wave which has a frequency. And therefore, if you want to locate the position accurately, then you will have to use a higher frequency light. Then you will be able to measure the position accurately to the extent of its frequency. And the moment you try to do that, that particular photon does contain some energy, and that will be absorbed by that electron, and therefore the electron will gain energy, its position, momentum will change, and therefore the momentum will become uncertain. And if you want to avoid that, then you have to use a lower frequency electromagnetic wave in order to see it. And the moment you do that, your position will become uncertain. You will not be able to measure it accurately. That is a kind of explanation Heisenberg gave, and that you might have read in some popular literature. But I can tell you that we now understand that explanation is not right. Because that explanation is based on our trying to observe it. We are trying to observe it, our observing it. So it is essentially the observer's ability or inability to observe the position and momentum. Their explanation was related to that. But we now know that this character is independent of our trying to observe it. That is innate to the material world. And what it actually means is that if the position is accurately determined means not somebody is determining that. It has a value. It has a definite value. Then the other one, to variables that do not commute with each other, the other one will not have a definite value. And if the other one has a definite value, this one, if B has a definite value, then A does not have a definite value. It's not that we are unable to measure it. It is that it does not have. So we need to understand it that way. It does not have a definite value. Now, this is somewhat difficult to comprehend. What do you mean by not having a definite value? In order to do that, in order to explain that, I will exemplify that. But another question came, that is, what about the energy time uncertainty? And I did not answer that question. I thought that I'll answer it sometime later. The reason that I did not want to discuss the energy time uncertainty in the same breath as this generalized uncertainty principle, that energy uncertainty is not obtained from this. Is not obtained from the generalized uncertainty principle. The reason is that in this case, A and B are two dynamical variables. dynamical variables that can be observed, and therefore they are represented by their parameters and all that. But time is not a dynamical variable. Time does not go up and down. Time is a parameter of the system, independent parameter of the system, and therefore that does not have a corresponding operator. Okay. The time energy uncertainty is not obtained from this. Let me delete this, and then it will be easier for me to work on. Yeah. The time frequency, time energy, so sigma T, sigma E, it may look similar, but it does not follow from the generalized uncertainty principle. Then how do we understand it? Now, in order to understand that, let us go a few different ways. Firstly, let us take a very common sense way. Suppose I make a sound like this. Have you heard the sound? Yeah, it was a tick sound, right? I made with a pencil on my table. And if I ask you, when did that happen? At which the sound happened, you can easily measure that, provided you select a 0 time on your wristwatch, and then you can say that it happened 3 seconds later. So time is defined. Time is determined. It has a value. But if I ask you what was the frequency of that sound, you suddenly realize that you cannot say whether it was sa, re, ga, ma, what. We don't know. We don't know because a sound like this is an instantaneous sound, and the instantaneous sound, it does not have a definite frequency. It does not have a definite frequency. If you want to find out its frequency, what will you do? If you have a sound coming, you will take the data from there and you subject it to a Fourier transform. And if you subject this kind of a impulse function to a Fourier transform, you will find that it contains all the frequencies. So the frequency, it does not have a difference. Do you realize that time and energy, frequency and energy are related to each other? You know that. So time and energy are such variables so that if the time is determined, has a definite value, energy does not have a definite value. Similarly, if I say it has a definite frequency and therefore energy is also given. But if I ask you when did that happen, suddenly you will realize that happened for a long time, a span of time. And therefore, when did it happen? That specification of the time makes no sense because it happened over a long time. There was no specific time at which it happened. So this is a typical example of uncertainty. And when you extrapolate the idea to the position momentum uncertainty, there also you have to think in the same line that if this one has a value, that one does not have a definite over a range. The energy time uncertainty can also be understood. What I explained with was a commonplace day-to-day event. It's actually related to the way Fourier transform is understood. But then, what about the quantum mechanical perspective? Well, in the quantum mechanical perspective, I will not derive this equation. Will not. I'll just illustrate because it doesn't follow from the generalized uncertainty principle. And that's why you will not. It is sort of a heuristic understanding. But it has implications. For example, in a harmonic oscillator, if the psi function, psi, at a 0, say, is the same as, say, psi 1. Psi 1 means the first excited state wave function. eigenfunction. Then you know that that particular state, the energy is defined is E1, the energy corresponding to the first excited state. So energy is defined. Then we'll ask the question, what is the time then? Well, you'll realize that if the state is this, then it forever remains in that particular state. If it is an eigenstate, eigenstate. So it remains forever unchanged in that eigenstate, means the time at which this particular value of E was there is undefined. It is a very long time, and therefore you cannot define the time. So if you put if the value is known, then the uncertainty is 0. Therefore, this value is 0. And therefore, this has to be infinity. Right? So that is what is obtained when you say that if I have the initial state in a eigenstate, then it forever remains. So this is the first case. Second case, you consider psi at 0 is half of psi naught plus, sorry, 1 by root 2 it will be 1 by root 2 psi 1. A situation like this means it has two possible values. If you make an observation, it could be E1, E0 or E1. And you do not know which one will come. Therefore, there is an uncertainty in the measured value of E1, and then uncertainty of the order of, so sigma E is of the order of E1 minus E0. Since I'm not talking about any particular one, put a I mean, if you consider any two, psi m, psi n, you would like to put a mod because you don't know which one is bigger. And then, what about the time? You see, once I considered it and worked out the time evolution of that, and you saw that the time dependent part, I can write it now. I have to go back to that particular day's lecture. Let's see, somewhere, yes. We had obtained, let me get some space. We had obtained that psi star xt psi xt, that was ultimately obtained to be a1 square psi 1. We had done it for psi 1 and psi 2 that day. It doesn't really matter. It's basically the same thing. Plus square psi 2 x square. Now plus the time dependent parts, plus a1 star a2 psi 1 star x x e to the power I e1 minus e2 t by h cross plus a2 star a1. Open the class note of that page, you will see you don't have to write it all over again. This is what we had obtained that day. So you see, when this thing actually oscillates, we have seen that it oscillates, its characteristic time is related to I omega t, e to the power I omega t, omega gives the characteristic time. So omega is E1 minus E2 by h. So the characteristic omega is E1 minus E2, it's mod because this E1 minus E2 and E2 minus 1 by h cross. So this gives the frequency you can obtain from there. By f is t. So if you do that, you will find that the time, characteristic time, is related to E1 minus E2 by h cross. Okay. So which means that if there is an uncertainty to the extent of this, put E1 minus E2 then. 1 E2. So there are take this one. Since I've written E1 and E2 there, let me do the same thing. So you'll get a time will be related to this E1 minus E2, which means that if the uncertainty in energy is of the order of E1 minus E2, then your uncertainty in time should be such that this equation is satisfied. Okay. This has other impacts. For example, inside a nucleus, the nucleons are there, the protons and neutrons, and they are bound by a force. Now, that force, now we understand, is mediated by certain particles. If you want to visualize, it is like, suppose I have a river and there is a boat and there is a guy standing on the boat. And there's another boat here and there's another guy standing on the boat. And suppose this guy throws a ball at this guy. So what will happen? The moment he throws the ball, he will feel a recoil, and that therefore the boat will move to that side, right? And then this guy catches the ball, therefore the energy in that ball on that, and he moves this way. So if somebody is observing this particular event and does not know a ball was thrown, he will feel that there was a repulsive force between these two boats. Okay. Now we know that at least quantum field theory, that whenever there is a force between two bodies, it is actually mediated by certain particles, and the character of being able to throw and receive photons is called charge, and so on and so forth. But in this case, in case of inside a nucleus, the nucleus exchange certain particles, pions, these are called, and the pions have, unlike the photons, pions have mass. So when one nucleon releases a pion towards another, then it has affected the energy conservation rule by extent of mc square. M is the mass of that particle, mass of the particle that is thrown, of the mediating particle. So the energy conservation rule has been violated. But then this is it must be absorbed by the absorbing particle within a time, so that this equation is not violated. Therefore, it must be caught by the particle within a time. That is, so this is the uncertainty in the energy, and therefore, if the uncertainty energy is put in this side, the time within which it has to be observed, and that is the characteristic time within which it has to be observed. absorbed. Now that within that time, the particle travels a distance. That is the time times c. So that distance is the characteristic distance within that this particular force works. So all that can be obtained simply by taking recourse to the time energy uncertainty principle. Okay, these things in detail you will learn in the next semester's course, probably the next semester, the quantum field theory. I'm not going into the details of it, but you can see that the uncertainty principle has very profound implications. Okay. Good. So this is the amount I wanted to talk about the uncertainty principle, but I did not want to talk about the energy time uncertainty in the same breath with this. This is not obtained from there. Okay. Good. Let's now go to the next topic. Let me clear this. Okay. Well, in exposing the state vector formalism, I was going in stages. In the first stage was to get you psychologically accustomed to that a function which does not look like a vector at all has some characters in common with the vectors. So that was what we did, and I tried to get you used to a notation something like this, the bracket notation, psi1, psi1. So this kind of notation, which actually implies minus infinity to infinity, psi1 star psi1 dx. And I want try to get you accustomed to this compact. And at that stage, I did not want to get into the next stage or mixed stages, so that only when you get somewhat accustomed to this concept, we go to the next stage. Well, today that time has come because the last week was spent in doing whatever could be done. I tried to figure out what can be much of idea. I figured that the generalized Ehrenfest principle, generalized uncertainty principle can be derived without going any further into the state vector formalism. So we did that, but now we need to go forward. And that going forward would entail not only figuring out the functions have some things in common with vectors, but also being able to treat functions as vectors. I'll come to that. But before we come to that, let's clear out one issue. Here, this is the bra part, here is the ket part. Put together makes the bracket. Right? Now, if we put them in the opposite order, the ket first, and then the bra. Does it mean anything? Well, looking at this, you might feel that this is looking for something here, and this is looking for something there, as if something is amiss. We don't. So in order to figure that out, let us do what sort of it is asking for. Let us put, say, psi here and try to figure out what it means. What this part means is essentially the overlap psi with the first excited state eigenfunction. So this is essentially, this part is essentially minus infinity to infinity. Sorry, I did not put this. Psi1, psi. Okay, I'm avoiding this x. I can always put that x. So this is the overlap integral. And in our mind's eye, I had tried to get you accustomed to the idea that if my psi is this vector, psi, let me make a bigger one. Is say this one. Then this is nothing but this much. It's like a projection. The amount of the projection, that means the magnitude of the projected vector. And what is this psi 1? It is the unit vector in the direction of this, because this is these are supposed to be vectors that are normalized. So this one is actually supposed to be equal to 1, a unit vector in that particular direction. So what is happened is that this part gives the component, the magnitude of that component, magnitude of the projection, and this one gives the unit vector. Therefore, the whole thing is this, right? So I can see that this has a meaning. This part has a meaning. It means that it is an operator which, when operated on any vector, any function psi, gives the vector that is in the direction of this, but whose magnitude is equal to the projection of psi into that psi 1. Okay. Therefore, this is called the projection operator. This is a projection operator. Okay. Let me clear this so that it's not cluttered. Okay. So this is the projection operator. Now suppose I have a series of these psi's, which means there is a ground state eigenfunction, the first excited state eigenfunction, the second excited eigenfunction, and so on and so forth. So then I can always write psi in terms of psi is equal to, say, C naught psi naught plus C1 psi 1 plus C2 psi 2, sorry, and so on and so forth. And there will be an infinite number of. You notice that how did you obtain this, or how did you obtain this full thing is nothing but the projection of psi onto the psi naught. This one is the projection of psi onto the psi 1, and so on and so forth. So, nothing but psi naught psi plus psi 1 psi all that. So this is nothing but sigma 1 to n, depending on how many are there, and this might be as well infinity. This is psi n. I'll put 1 to infinity because normally that's true. N psi. Okay. Now you notice I had started with psi. I had operated with an operator. I got psi, which means that this operator, this whole thing, is nothing but the identity operator. So the identity operator is nothing but a summation of all these projection operators. Okay, and this is something that we'll use again and again in the future classes. So just keep in mind that is nothing but an identity operator. Okay. With that background, let us go ahead and jump straight into the state vector formalism in a little more detail. Yeah. Any question?
Hello.
Yes.
Hello.
Question? Yes. Yes. Ask.
Sir, can you return back to that screen now, which you just erased? Can
Eh,
it all come back?
let me see if it allows me to do that. Yeah, it has allowed me to do that. That's good. Yeah.
Yeah. So, sir, how did you write the second equation? Like when you first wrote psi as C naught psi naught plus C1 psi 1, then how did you write the second step?
This is the second step. Yeah, the C naught is nothing but the C naught is nothing but the magnitude of the projection of psi or C1. Let done it was psi one. C1 is is nothing but the projection of psi onto the psi one vector. So C1 is this magnitude, right? And then it is multi.
Isn't
Yeah.
isn't C1 complex? So do we take C1 as is C1 as a projection or mod C1 square as a projection?
Wait. C1 can be complex, yes, and
So
these ones are can be complex numbers. These ones definitely can. So it is a complex valued coefficient multiplying this vector. Okay. So that way it goes on, and this is what we represented as psi naught. Or let's do it one reason because that's what we have drawn. So C1 is nothing but this one. Okay. Sorry, this
okay, sir.
I have to write it correctly. This is not this psi. It is a capital psi. So C1 is nothing but this. I'm not meaning that this might yield a complex number. Fine, that's okay. And this is the psi1 here. So all this is equal to this. That is how we wrote it. Is that clear now?
Yes, sir.
Yeah. And it is these are in general complex numbers. You are right. Okay. Now can we go back now? Let me delete this. Yeah.
Sir,
Yeah.
sir, I have a doubt about the time energy uncertainty example you gave.
Yeah.
So I understand that if you give an impulse, it should be the combination of all possible frequencies. But what if we just play, like, just say play a piano chord? So that will have a definite frequency, right?
Yeah.
So
But
and we
piano
can
chord
measure
actually
both the.
goes for some time. It's not a instantaneous sound.
But sir, let's say we play a key on the piano.
Mhm.
It will be instantaneous, right? If we
No,
can make it.
no, it will go on for some time. Otherwise, you will not be able to hear any particular note. You will be able to particular tick. It has to go on for some time, and then only you will be able to make out a note.
Okay. So we can't play a certain frequency at an instant.
You cannot. It has to ring for some time, and then only your ears will be able to make out a particular frequency.
Okay.
Okay.
Thank you.
Yeah. It's not only piano, all pluck instruments. Yeah. It has to go for some time.
Okay.
Ultimately, something vibrates,
So,
and
sir,
that vibrates some time.
isn't this analogous to the explanation that was given initially to for the X and P uncertainty?
Yeah.
So,
Yeah.
like it again comes down to the to our inability of measuring things, like
No, it
what you
does
are
not. It
saying.
does not. It does not. It does not. When you have sound, that means it is just a tick. That does not have a definite frequency. Does not have. It's not that our inability to measure. It does not have a definite frequency. Is it clear now?
Yes, sir.
Yeah. It does not have a definite frequency.
Sir, I have another doubt
Yes.
regarding the same topic. Yeah. So,
Yes.
so, so in the example of the harmonic oscillator that you had given, which was an equal superposition of phi 1 and phi 2, phi
Yes.
0 and phi 1.
Yeah.
So there you calculated the omega, and from there you said that we can calculate the frequency, and from there the time period.
Yeah.
And you sort of said that we can in delta, like sigma a sigma t greater than equal to h cross by 2, we can substitute this delta t by capital T. Is that what you implied?
No, 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 no,
Okay.
no, no. I said that energy has an uncertainty that was of the order of mod E1 minus E2. And I said that time also has an uncertainty because the wave function oscillates. And characteristic time out from I wrote from that equation, and it has a value which is related to mod E1 minus E2 by H cross. Right? That was the frequency. From there, you have to find, that was the omega, angular frequency. From there, you have to go get the frequency and 1 by frequency. So from there, you can get a characteristic time of the system. And these two, the uncertainty, or this is the uncertainty in time, measure of uncertainty in time. Characteristic time is measure of uncertainty in time. So these two must be related by an upper bound, h cross by 2. That's what I said.
Okay, but I still don't get the physical notion of what it means by uncertainty in time in this particular case. Like I understand that it's there is some kind of an oscillation due to the e to the power
Yeah.
I E1
In
minus
case of
E to the-
uncertainty in time, you are asking the question, when did it happen? Okay. When did it happen means I have tried to make a measurement, I have found E1. And I'm trying to find out when did it happen. Right.
Okay.
And this since the with the time period of that, I'll
Yeah.
not be able to specify time within that accuracy. Okay, so time has also a sort of characteristic uncertainty
Okay.
because it oscillates.
Okay.
Okay, yeah.
Thank you, sir.
Now, try to go into hardcore representation of functions by vectors. Essentially, what we are saying is that suppose I have a vector. That is our mental image of a vector, say V. Now, this is also represented as, say, V1, V2, V3, as a collection of numbers. How do we do that? We do that, or we can do that, only when the coordinate axes are. So you have the coordinate axis defined. My drawing is bad. Let me do it in a better way. Let me do this in a better way. Go there. Okay, now I have, say, a vector like this. I have a vector, and then we can define that only when we can draw projection like this. And then this part will be our V1, this part will be our V2, this part will be our V3, and then we can write this as a vector like this, right? Which means that if you have we can write it as a column vector by only when we have the coordinate axis or the basis defined, And the moment the basis is defined, a vector like this takes a form of the vector like this. Here. Now, in quantum mechanics, we have the psi function, which is given as a linear combination of the I'll put in the vector form. And so on and so forth. Which means that, and these ones, these psi naught, psi 1, and so on and so forth, these are mutually orthogonal and normalized vectors, orthonormal set of vectors, and therefore these can also be treated as basis. Therefore, this has a character similar to this, where we can say that I have a vector, a set of coordinates defined by, this is my psi naught, this is my psi 1, this is my psi 2, and then the psi is nothing but a vector which has components. It will have similar components, and this is my, sorry, this would be psi naught. So this is C naught, this one is C1, this one is C2, and so on and so forth. And yes, there will be infinity of them, but that doesn't matter. The picture is the same. The mental picture is the same. So the functions that we have been dealing with so far, initially we said that it has a character of vectors, but now you realize that for all practical purposes, the whole thing, the whole psi, can be written as a column vector of C naught, C1, C2, and so on and so forth. Is that clear? So this actually leads us to the whole body of knowledge known as the state vector formalism. Okay, so it is not only writing the integrals as brackets, but actually picturing these as column. Right? Great. So,
Excuse me, sir.
yes.
So when you have these, Cheyens, which are supposed to be your basis vectors, are they supposed to span a particular function space, or are they spanning the general function space? I mean, are they supposed to span only the functions of that particular given state, like all the wave functions of that, or can they be the basis of any kind of a function?
No,
as long as
that one, because these are dependent on the kind of potential or the Hamiltonian function you consider. The basis set for the infinite square well were not the same as the basis set for the harmonic oscillator well. So only when you have the setting well defined, I have a harmonic oscillator. For that, I have obtained those mutually orthogonal and normalized vectors that can be as the base used as the basis. Then I can express psi as a function of that. But this is not the unique choice of basis. We can have a different choice of basis also. I'll show those things. Okay. So normally we choose depending if it is an energy basis. For example, this is in the energy basis because these are the energy eigenfunctions. Okay. These are the energy eigenfunctions. Each will have an energy value as the eigenvalue. Therefore, this way of writing it, we'll call it that psi is now expressed as a vector in the energy basis. And depending on what you want to observe, you might express it in other bases also. I'll come to those things later. Okay. Presently, since we have already done at least 3 different cases, the infinite square well, the finite square well, oscillator well, therefore we know what these are. and it will be easier to start from there, and we'll go into the other basis also. That means basis, choice of basis is not unique, but this is the natural choice of basis if I am expressing psi, the function of the energy, or as a linear combination of the energy eigenfunctions. Clear?
Yes, sir. Thank you.
Let's go ahead. Suppose I have a vector v, then the way I have written, I'll write it this way: column vector to say vn. And there is another vector w, which is way. Given a basis, we are able to write it this way. Otherwise, we cannot write. We can write it as a column vector only when we have a basis. Okay. Now, how were these obtained? These were obtained as the projections of the vector onto different axes, right? So these are the projections. And when we consider a situation like this, these are also the projections. That means the psi was there, this vector. Its projection onto the individual eigenfunctions. These eigenfunctions are now considered the basis, and these basis, the projection of this eigen. So what is say C naught? C naught is the projection of psi naught. What is C1? C1 is a projection of psi onto psi 1. So on and so forth. Now, when we consider this, just a few minutes back, somebody pointed out that these numbers need not be real numbers. These can be complex numbers. So in our case, we are considering situations where these numbers can be complex numbers. And this is where our old notion of a vector looking like this and all these are real numbers, that will have to be generalized into a situation where these complex numbers. So we consider a situation where these numbers are complex numbers. If that be so, then how can we write this? Now, notice that whatever in the integral form, this part had to be starred, conjugated. And this is similar to a dot product. And therefore, we have to write it as V1 star, V2 star as a row vector. Times W1, W2. Then you see V1 star, W1, V2 star, W2, so on and so forth will happen, and it will get the structure of the proper dot product between these, something that we already know you're comfortable with. So this implies that when you want to talk about, if you have the V given like this, then it is already written. So our bra, equivalent bra of this will be the conjugated row vector. So we come to the conclusion that the bras are row vectors, kets are column vectors. When you want to put them together, you get a bracket, and that is nothing but the dot product of the two vectors. Okay. Now, how did we obtain components? We obtained the components, as a projections. And we have just seen that the components can, therefore, projection can be obtained by the projection operator. So our V can be obtained as summation I and the vector V. Okay. So this is summation I, means this whole thing is the operator. I, and each of the components are obtained by, say, the first one, V1 is 1, 1, V. 1 means the first one. V2 is 2, 2, and so on and so forth. That is how we obtain these components. Okay. We actually write, when we actually write V, it is, we have written it as V1, V2, Vn. This is nothing but writing V1 is the times a vector which is 1, 0, 0, 0, dot, dot, plus V2 times another vector which is 0, 1, 0, 0, dot, dot, plus V3 or Vn. And then it is Vn times 0, 0, 0, dot, dot, 1. So you see, when we write this, it is actually, see that these are the basis vectors and these are the components. So the vector is written as a linear combination of the basis. And in case of quantum mechanics, these will be nothing but the eigenfunctions. So the eigenfunctions will also be picked as vectors like this. Okay. Now 3 minutes are left. I have to stop now. We'll continue with this next class. But if there is any quick question, you can ask. Otherwise, we'll go to the next class.
Sir, V1, V2 are the scalar components, right? In that case, there should be just the inner product.
Yes.
So,
Yes,
but you have
it,
written
no.
the projection operator on V. So that will be the vector component, right?
Oh, sorry, sorry. Yeah, you're right. You're right. So it is only this part. Sorry. Yeah, you're right. So these are the scalar components, but these can be complex numbers. There's a point I was making. So these are the projections, these numbers, but these numbers can be complex numbers. You're right.
And sir, I had another question on this energy time thing. Should I ask it now or should I ask it next class maybe?
We have 2 minutes. If you have any class, then you have trouble, but otherwise you can ask.
Okay. So the thing is that you said that so the energy time uncertainty is related to the fact that when does a particular thing happen? Suppose we measure the energy and we get E1. When did that happen? But this uncertainty should be inherent. It should not be dependent on measurement or something like that. So far as I understand.
Yes.
So without going into when I measured E1 or when I measured E2, can we talk about uncertainty like delta A, like sigma A, sigma T? Then how, without invoking that sense? Yeah. Okay.
But the problem of the energy time uncertainty is, in order to understand it, look at it from the point of view of Fourier transform. If you have an impulse function, it does not have a definite frequency. It is a combination of all possible frequencies. If it exists for a very long time, then you can have a definite particular frequency. It is essentially this applied in particular topic, but essentially.
Okay, sir. Thank you.
Okay, let's stop today because we have past time.